Hello and welcome guys to today's video, and we are going to be solving the following problems under Bernoulli's differential equations. We have y prime plus y tan x is equal to y cube sec to the power of 4x. So y prime minus 2y tan x is equal to y squared tan square x, and y prime plus y is equal to y to the 4 exponential x. And finally, y prime plus y is equal to y cube into x minus 1. So let's dive into the solutions right away. Okay guys, in problem 1 we have y prime plus y tan x is equal to y cube sec to the power of 4x. So this is how we are going to do that. To solve it, you have y prime plus y tan x is equal to y cube sec 4x. You're going to divide through by y cube. Dividing through by y cube, you're going to have y to the minus 3 y prime, and plus, of course, when you divide y by y cube, you're going to have y to the power of minus 2 tan x is equal to sec to the power of 4x. Is that okay? So this is what we have. So what do you do next? Of course, remember this is acting as our y raised to the power of 1 minus n. If you watched the introductory video to this Bernoulli's differential equation, so, and of course this y prime is the y dx, so let me just put it to us straightforward like this, that this is y to the power of minus 3 dy dx plus tan x, then y raised to the power of minus 2 is equal to sec 4x. So I'll call it equation, this is equation 1, the original equation. This is equation 2 over here. So you're going to say let a be y raised to the power of minus 2. Always attack the variable here, always attack the modified form, always attack the y to the 1 minus n, and in this case our n is 3 according to what we have over here. Okay, so always attack this one, try to replace it with another variable of your choice. I'm using a in my case, and a is a function of x. So the a dx, remember chain rule, the a dx is actually the a dy times the y dx. So this the a dy means that I'll differentiate this one as if a was just only a function of y. This will give me minus 2y to the power of minus 3. Then I'll now attach this multiplier dy dx and dy dx. Okay, so this is my dA dx. So again, something is interesting is happening in this dA dx. I can see that this dA dx looks like this first term in equation 2. The only difference is this factor of minus 2, and this factor of minus 2 is still 1 minus n. Okay, still 1 minus n. So what do I have to do? I have to try to make this equation 2 have this particular factor of minus 2 in this first term, and the way I can do it is by multiplying equation 2 through by the factor minus 2. So you multiply equation 2 by negative 2 throughout. Okay, so if you do that, you're going to get minus 2. That implies minus 2y dy dx. Okay, so minus 2 tan x y to the minus 2 is equal to minus 2 sec to the 4 of x. So this is equation 4. So if you just modify equation 4 a little, what you're going to get is minus 2y minus 3 dy dx, then plus minus 2 tan x y minus 2 is equal to minus 2 sec 4x, like this. So 4a. Now recall that a is equal to what? Y to the power of minus 2, and our dA dx from equation 3 is minus 2y to the minus 3 dy dx. So some terms in this equation 4a can be replaced, such as this one. For example, this one will be replaced with dA dx, while this one will be replaced with a. So therefore equation 4a becomes dA dx plus negative 2 tan x, then instead of y to the minus 2 you have a is equal to what? Minus 2 sec 4x. Is that okay? So now we have converted this to a linear form. We have converted it to a linear form in terms of a and x. So we are going to solve this linear differential equation without wasting much time. So first of all, the integration factor if is exponential integral of p, okay, the modified p of x dx, and the modified p of x dx is actually this guy over here, as you can see him, okay, which is negative 2 tan x. So this is exponential integral of minus 2 tan x dx. So let's go together. This is exponential, remove the minus 2, integral of tan x. Tan x is sine x over cos x dx, and this is exponential. I'll have to send the minus sign inside, so minus sine x dx over cos x. So our integration factor is exponential to integral of, so minus sine x dx is d of cos x. If you've been following my series, I was able to establish that if you differentiate cos x, you're going to get minus sine x. Okay, so d of cos x is minus sine x dx. That is why you see me replacing this minus sine x dx with d of cos x over here. And anytime you're integrating 1 over something with respect to something, you're going to get ln something, okay, plus whatever you want to have as a constant of integration. But remember, in integration factor you are not supposed to take note of the constant of integration. So we have exponential 2, so integral of 1 all over cos x d cos x gives me ln cos x. So this is exponential ln cos squared x. Okay, so our integration factor becomes cos squared x. So the rule we are using is exponential ln f is equal to f. Exponential ln f is equal to f. So this is the integration factor. So now that you've gotten the integration factor, how do you work with it? So you now say a times integration factor is now going to be equal to integral of the augmented q times the integration factor dx. Okay, so a times cos squared x is going to be integral of the augmented q is now this guy over here. Remember, the original q is just sec to the power of 4x, and the augmented q is the q that is multiplied by the factor 1 minus n, where n is 3 in this case. So we now have negative 2 sec 4x, and the integration factor is cos squared x dx. So let's see what we're going to get. So we have a cos squared x is equal to, if I bring out the minus 2, you have integral of sec 4x cos squared x dx. So if you can recall that sec x is the reciprocal of cos x, in other words, sec 4x is the reciprocal of cos 4x. So you now say a cos square x is equal to minus 2 integral of 1 over cos to the power of 4x. Then you now have what? Cos square x dx. Is that okay? So let's see what we get when we do this. So we now have a cos squared x is equal to minus 2 and integral of 1 over cos squared x dx. Is that okay? So we're now going to have a cos squared x is equal to minus 2. Then integral of 1 over cos square x is still integral of sec square x dx. Okay, just like do the conversion. Okay, so they're trying to tell me that sec 4x times cos squared x is actually sec squared x. Okay, if you do the mathematics. So of course you know that the integral of sec square x is actually tan what? X. Thank you very much. So a cos squared x is actually minus 2. Then I'll now have what? It's minus 2 tan x plus c. Is that okay? When you integrate sec square x, you get tan x. So if we divide through, we'll have a is equal to c minus 2 tan x over cos squared x. So don't stop there. Recall that a is equal to y raised to the power of minus 2. Is that okay? So you now have y raised to the power of minus 2 is equal to what? C minus 2 tan x over cos squared x. So in other words, when we take the reciprocal of both sides, when you take the reciprocal of both sides, what happens when you take the reciprocal of an indices to a negative power? Of course, it becomes positive. So y squared will now be cos squared x over c minus 2 tan x, like this. So this is what I would leave as my general solution for this particular problem. Someone else can take it further by saying y is square root of cos squared x over c minus what? 2 tan x. You can actually put your plus or minus if you want. So if you distribute the square root, you have plus minus cos x over root c minus 2 tan x. So you can actually leave it like this. Okay, and for this particular stuff to be valid, c minus 2 tan x should be greater than 0. Okay, so this particular case, so c should be greater than whatever we have for 2 tan x, in other words. So don't worry about all these particular ones over here. I'll rather we stop somewhere here. Okay, here is actually a good way to stop, and if you still want to take it further, there are like infinite ways of expressing your answer. But once you've gotten up to this point, at least the examiner or whoever is attending to your problem would believe that at least you've gotten to a good point, okay, in obtaining solution of this particular Bernoulli differential equation. So we're going to be looking at another problem, but I hope you have understood so far the dynamics of solving the Bernoulli differential equation using problem 1, which we have seen above. So we're going to be going to another problem, so stay tuned. Okay guys, here we are before problem 2. We want to solve y prime minus 2y tan x is equal to y squared tan x. So I'm going to rewrite the equation changing y prime to dy dx, and minus 2y tan x is equal to y squared tan square x. So call this equation 1. So as usual, what's the first thing to do? So you divide through. Since this is a Bernoulli's problem, divide through by y squared. So dividing through by y squared, you have y to the minus 2 dy dx. Okay, then minus 2. So y divided by y squared should give me y to the power of minus 1. So tan x, y squared divided by y squared cancels out, tan square x. So this is equation 2. So of course non-linear, the degree of non-linearity n is actually 2 in this case. So we are going to what, exchange this factor. So let me just be dynamic a little. So let me say something like z be equal to what, y inverse, and z is a function of x. Okay, let z be y inverse in my assumption 3. So z is a function of x. Now if we differentiate dz dx, we're going to use chain rule. Dz dx is dz dy times dy dx. Okay, see how these two will cancel out, leaving you with dz dx. But we're not going to cancel it out literally speaking. So dz dx is dz dy. You're going to differentiate z as if it were a function of y. So that will give me minus y raised to the power of minus 2. Then we're now going to take dz dx, which is going to give me after differentiating dz dy, you're going to attach this multiplier dy dx. Okay, so the reason you're doing it is because z is a function of y and y is a function of x. So this is how you obtain your dz dx. So this is 3b. Now examining closely equation 3b and equation 2, look at the first term. The first term of equation 3b and equation 2, you will discover that equation 3b is closely related to equation 2. That is the first term, literally speaking, and the only difference between the first term in equation 2 and equation 3b is the presence of this minus sign, meaning that I can actually make equation 2 have a first term that looks like equation 3b by multiply equation 2 by minus 1 throughout. Okay, so when you multiply equation 2 by minus 1 throughout, let me be looking at equation 2. I'll now get minus 1 times y to the minus 2 dy dx is a minus. Okay, so minus 1 times 2, okay, it's actually plus 2y inverse tan x, and minus 1 times tan square x gives me negative tan squared x. So this is an equation 4. Now that we've multiplied everything through by minus 1, you will now agree with me that the first term in equation 4 now is now corresponding to what we have in equation 3b. So the first term in equation 4 can be replaced with the z dx, and this particular term over here can be replaced with z itself. So y inverse, or y raised to the power of minus 1, can be replaced with z. So what we'll now have is dz dx, okay, plus 2 tan x, I just rearranged it, z is equal to negative tan squared x. Okay, this is equation 5. So this is the linear equivalent of the Bernoulli's equation. So to solve it, of course, our integration factor will be exponential integral of the modified p of x dx, and the modified p of x dx this time around is now going to be, we have 2 tan x dx, which gives me exponential 2 integral of, what do you have, sine x over cos x dx. So in still solving, you have if is equal to exponential. Okay, so you will see that when you differentiate cos x dx, you're going to get negative sine x. So d of cos x is actually negative sine x dx, but what I can see is just sine x dx, so I have to introduce a minus sign there. So in introducing a minus sign, I'll have to put a countermeasure by putting a minus here first, and I'll now put minus sine x over cos x dx. So now I have successfully introduced it. Of course, minus times minus will give you plus, and you return back to the original way it was. So this is exponential minus 2 integral of 1 over cos x. So minus sine x dx is d of cos x. Is that okay? So remember, integral of 1 over something, the something is ln something. Is that okay? So integral of 1 over cos x dx is going to give me ln cos x. So you have exponential minus 2 ln cos x. This is exponential ln cos minus square x, and this is cos negative 2x. Okay, remember that exponential ln f is equal to f. So these are the identities that we are working with to simplify our integration process. Now that we've gotten the integration factor, you now want to say that sorry about this, your z multiplied by integration factor is equal to integral of your augmented q of x times integration factor dx. Okay, so having gotten up to this point, you now get z multiplied by cos negative 2x is equal to integral of our q of x, that's the augmented q of x, according to equation 5. See that the augmented q of x is minus tan square x, so you now have minus tan square x multiplied by integration factor, which is cos minus square x dx. Now note, cos negative square x is still the same thing as 1 over cos square x, and this is sec square x. So I'm going to replace this with sec square x. So z is actually multiplying sec square x here, and this is negative integral of tan square x times sec square x dx. So the earlier you see this, the better for you. Now to carry out this integration, I want you to note that when you differentiate with respect to x tan x, you're going to get sec square x. So in other words, d of tan x is actually what? Sec square x dx. D of tan x is sec square x dx. So this sec square x dx here can be replaced with d of tan x. So z sec square x is equal to negative integral of tan square x d of what? Tan x. Okay, so this is what this hand becomes. So on this particular side, what I now have is integral of something square d what? Something, and this is actually something cube over 3 plus c, if you remember your rule of integration. So we have z sec squared x is equal to minus the something cube is now my tan cube x over 3, then plus constant of integration. So my z sec squared x is now going to be what? Thank you very much. C minus what? Tan cube x over 3. So what they're now trying to tell me invariably is that you have to recall that z is actually y minus 1. I hope we remember from equation 3, z is actually what? Y minus 1. So if you make this recalling, you're going to get sec squared x over y is equal to what? C minus what? Tan cube x over 3. So you can actually rule the pen here. So this is a good point to stop. Anyhow further you might want to take it, you can actually go ahead to push it that far, but this is where I'm going to stop. So sec squared x over y is equal to c minus tan cube x. So this is the solution for this particular problem. So we're going to be moving on to the solution for another problem. So guys, welcome to problem 3. In problem 3 we are looking at y prime plus y is equal to y raised to the power of 4 exponential x. Now to solve this problem, as usual, you convert your y prime to dy dx, then plus y is equal to y raised to the power of 4 exponential x. Call this equation 1. So the next thing is to divide through out by y raised to the power of 4. Then when you divide throughout, you get y to the power of negative 4 dy dx plus, now y divided by y to the power of minus 4 is y to the minus 3, and this is now going to give me exponential x because y4 cancels out. So this is equation 2. So what are we going to do next? So let's say let m be equal to y raised to the power of minus 3. So you can call this equation 3. So m is a function of x itself. So if you now want to find the m dx, since m is a function of y and y is a function of x, you're going to use chain rule. The m dx is actually the m dy times dy dx. So you're going to differentiate the m with respect to y first, which will give me minus 3y to the power of minus 4. Then you're now going to add this multiplier dy dx. So this is equation 3b. Now you're now going to observe, okay, that your equation 3b is just like almost equal to the first term in the equation 2. The only thing is this particular factor over here. So you're going to ask yourself, how am I going to introduce this particular factor in equation 2? And it's easy, just multiply equation 2 throughout by minus 3. So in multiplying equation 2 by minus 3, you're going to get minus 3 y to the minus 4 dy dx, then plus, plus, let me put it, minus 3. So you have y to the minus 3 is equal to minus 3 exponential x, like this. Is that okay? I hope we are all together. Now you can now see now that at this juncture, this equation 4 is now transformable in terms of m. So the first term of equation 4 can actually be written in terms of the m dx, and the second term, the y raised to the power of minus 3, can be kept as if it was m. So this minus 3y to the power of minus 4 dy dx now becomes the m dx, then plus minus 3, then y raised to the power of minus 3 becomes m, and this is equal to negative 3 exponential x. So this is 5. So 5 is now linear. It's now a linear differential equation in terms of m and x, so that our integration factor in this case is exponential integral of our augmented p of x dx. Our augmented p of x is actually minus 3 dx, and this is exponential minus 3x. Are we good? So our m times integration factor is now going to be integral of our augmented q of x times integration factor dx, okay, according to the formula. So our m times integration factor will be equal to exponential, our augmented q of x is this one that we have over here, okay, minus 3 exponential x. So you have minus 3 exponential x multiplied by integration factor, which is exponential minus 3x dx. Are we good? So of course law of indices have to play a part here. So you now have m exponential minus 3x is equal to minus 3 integral of exponential x times exponential minus 3x will give me exponential minus 2x. So exponential x times exponential minus 3x is exponential x plus minus 3x, which is exponential x minus 3x, which is exponential negative 2x, okay, dx. So m exponential minus 3x is actually equal to, so you now have minus 3. When you integrate exponential minus 2x, when you integrate exponential ax dx, remember that you get exponential ax over a plus c. So you're going to get exponential minus 2x over minus 2 then plus c like this. So you're going to get m exponential minus 3x is equal to, we have 3 over 2 exponential minus 2x then plus c. So when we divide through by exponential 3x, we'll have minus 3x. M is equal to 3 over 2 exponential minus 2x divided by exponential minus 3x plus c over exponential what? Minus 3x. So this now becomes m is equal to 3 over 2 exponential x. So exponential minus 2x divided by exponential minus 3x, according to the law of indices, is exponential minus 2x minus 3x, and this is exponential minus 2x plus 3x, which is exponential x. Okay, so you have plus c exponential 3x. So the law of indices is 1 over e raised to the power of minus n is equal to e raised to the power of n. Okay, so this is m. So you have to recall that m is actually y to the power of minus 3. Are we together? M is y to the power of minus 3. So we have y to the power of minus 3 is equal to 3 over 2 exponential x plus c exponential 3x. So if you want to modify this, you can say two ways. Someone can say 1 over y cubed is equal to 3 over 2 exponential x plus c exponential 3x. Okay, so someone can leave his answer like this. Another person can come and say 1 over y cubed is equal to, when you take the LCM in this particular area, you get 3 exponential x plus 2c exponential 3x over 2, for instance. So you can now say y cubed, taking the reciprocal of both sides, is equal to 2 divided by 3 exponential x plus, let 2c be equal to a, for instance. You now have a exponential 3x. So someone can leave his answer in this particular form. So whichever one you want to choose, you're free to leave your answer in any of those forms. Okay, so this is the solution for this particular problem. I hope you learned all the steps. I hope you benefited from it. So let's move on to the last problem number 4. Okay guys, this is problem 4 and the last problem in our series for Bernoulli's differential equations. So in problem 4 we have y prime plus y is equal to y cubed into x minus 1. As usual, you're going to convert y prime to dy dx plus y is equal to y cubed into x minus 1. This is equation 1. Now you're going to divide through by y cubed. So dividing through by y cubed, over here you have y minus 3 dy dx plus y divided by y cubed is actually y to the power of minus 2, and this gives me x minus 1. This is equation 2. So which variable are we going to use to substitute in this case? So let's use a. So you now say let a be equal to y to the power of minus 2. Okay, equation 3. And of course a is a function of x. So you're going to obtain the a dx, and to obtain the a dx you need to remember your chain rule. Since a is a function of y and y is a function of x, the a dx will be the a dy times dy dx. Okay, so the a dy, differentiating this one with respect to y, gives you minus 2y to the power of minus 3, and it's actually minus 3 because when you differentiate you actually reduce 1 from the power. Okay, so when you reduce 1 from a negative number, the negativity increases. That's why it's actually taking us backwards to minus 3. Then you now have to multiply this by what? Dy dx. Okay, according to chain rule, dy dx. So this is 3b. Now of course you're going to examine 3b and the first term of equation 2, they are almost similar, except for the fact that a minus 2 is missing in this equation 2. So you're going to multiply equation 2 through by minus 2. So this is what we're going to get. We now have minus 2 y to the minus 3 dy dx, then plus minus 2 y to the minus 2 is equal to minus 2x minus 1. Okay, so this is 4. Okay, now that we have it like this, you can now agree with me that clearly this first term now looks like equation 3b. Okay, so the first term can be replaced with dA dx, while this particular term over here can be replaced with a. So therefore we have dA dx plus minus 2, we have a is equal to, so if you open the brackets here, you're going to get 2 into 1 minus x. That's if you use the minus sign to actually simplify this particular bracket. So this is equation 5. Now we have a linear differential equation here whose integration factor is exponential integral of the augmented p of x dx, and this is exponential integral of minus 2 dx, which is exponential minus 2x. Is that okay? Exponential minus 2x. Okay, this is your augmented p over here. Then of course your augmented q of x is now 2 into 1 minus x. So take note of that. 2 into 1 minus x. So what we now have is that our a times integration factor will be integral of my augmented q of x times integration factor dx. So let's see how that simplifies. So you now have a multiplied by exponential negative 2x is equal to integral of my augmented q, which is 2 into 1 minus x, times integration factor exponential minus 2x dx. So this is what we are going to get. We now have a into exponential minus 2x is equal to 2 integral of 1 minus x, then exponential minus 2x dx. So I'm going to teach you the biggest trick in integrations history. So you can actually pause the video and try to integrate this right hand side by yourself, but I'm going to show you a trick to integrate it very easily. I know you've seen something like this. So I'm actually dealing with a linear factor here, then I'm dealing with an exponential here. So whenever you're integrating a linear factor, okay, linear factor please, linear factor, or you're integrating some polynomials in terms of x, and you're a polynomial in terms of x, whether it's a linear factor or not, as far as it has some particular parameters of x, and whenever you're dealing with an exponential, the criteria for you to use this trick I'm about to show you is that this exponential must have a linear argument. So by a linear argument, I mean it should be the likes of exponential ax. I don't want to see exponential x squared or exponential x cubed, exponential, something like that. So the degree of x in this particular exponential must be 1. Then you can have some random polynomial here. Okay, you can actually use this trick, and this is how the trick goes, like this. So you can actually use your normal integration technique to integrate this, but I'm not going to use all of those ones. And the normal integration technique I'm actually talking about is integral of u dv is equal to u dot v minus integral of v du. So I'm not going to use that one, although you can still use it to verify the answer I'm going to get here. So if you have verified it, you can post a comment on the comment section and tell me how amazing this method I want to teach you is. So you're going to put the linear factor or the polynomial on this side, and you put the exponential on this side. Okay, so just draw a line to demarcate what we're about to do. So when you do it like this, you're going to be differentiating here and you're going to be integrating this side. Okay, so if you differentiate this one with respect to x, you get minus 1. Of course, differentiating 1, you get 0. Differentiating minus x, you get minus 1. Now when you integrate exponential negative 2x, you get exponential negative 2x over minus 2. Now I'll differentiate this one again, I'll get 0. So this is where this differentiation stops. When you get 0, you stop differentiating. Now when you integrate exponential minus 2x over minus 2, you get exponential minus 2x over minus 2 times minus 2. Is that okay? Which is exponential 2x over 4 invariably. So to round up the answer for this integration, you now multiply this term by this term and this term by this term, and I'm now going to subtract. Okay, so you multiply the first term times exponential negative 2x, so we'll get minus exponential minus 2x over 2 into 1 minus x. And remember, we are subtracting from the product of this and this, so there is a minus 1, then you now have exponential minus 2x over 4. So I'll now put my constant of integration. Oh, sorry about that. I'll put my constant of integration. So the answer for this particular integral is we'll have, I can use this minus sign to open the bracket again. I'll now have exponential minus 2x over 2 into x minus 1, then minus 1 times minus 1 is plus. I'll now have exponential minus 2x over 4 and plus c. So this is the answer for my integral, this particular integral over here. So that's what we're going to write in this place. So writing it in this place, I'm now going to get a exponential minus 2x is actually equal to 2 open brackets exponential minus 2x over 2 into x minus 1, then plus exponential minus 2x over 4 and plus c. Is that okay? So a exponential minus 2x is equal to, opening the bracket with 2, you have exponential minus 2x into x minus 1, then plus exponential minus 2x over 2 and plus 2c. Okay, you can let 2c be equal to a, for instance. So a exponential minus 2x is equal to exponential minus 2x into x minus 1 plus exponential minus 2x over 2, then plus a. So if you divide through by exponential minus 2x, a will be x minus 1, then plus 1 over 2, then plus a divided by exponential minus 2x. And if you wrap this up, you're going to get a is equal to x minus 1, okay, then plus 1 over 2, then you now have plus a exponential 2x. Of course, when this one comes to the numerator position, the sign changes. So a is now going to be x minus 1 plus 1 over 2 gives us what? Thank you very much. It gives me a minus 1 over 2, then plus a exponential 2x. So you have to recall that a is equal to what? What is a? Is it y to the power of minus 2 or y to the power of what? Minus 1. So which one? Okay, so a is y to the power of minus 2 from your equation 3. So a is y to the power of minus 2. So in other words, y to the power of minus 2 is equal to x minus 1 over 2 and plus a exponential 2x. So one person can give his answer in this way: 1 over x, sorry, 1 1 over y squared is equal to x minus 1 over 2 plus a exponential 2x. Another person can leave his answer in this way, that 1 over y squared is equal to, I'll use the LCM to simplify, giving me 2x minus 1 plus 2a exponential 2x over 2. So if you take the reciprocal of both sides, y squared is equal to 2 over 2x minus 1 plus, let me call this one k exponential 2x, where k is equal to 2a. So someone can stop here and someone else can actually stop here. So however you stop, it's actually okay, as far as you understood the basic principles that brought you up to this level. You can actually stop in any of these points that you want. So this is about Bernoulli's differential equation. I hope you learned a lot. Hope you learned new ways of solving this particular problem. Our cool integration trick that we did over here, I hope you understood it perfectly. And I will say this is it for now. So in the next series, we're going to be jumping into exact equations. We're going to see how to tackle exact equations and the solutions to exact homogeneous differential equations. So thank you for watching. Please stay tuned, like, subscribe, hit the notification button, share this video to your friends. I'm sure it must have been beneficial to you. It will also help them. To all undergraduate students, to all who love engineering, mathematics, to all who want to learn new ways of solving their problem. And if there's anything you don't understand, don't forget to leave comments, leave a question for me, and when I see it, I'll attend to your problem. So thanks once again for watching, and take good care of yourself. Safe.